We are in Unit 11, and this is Notes 6. These are the last notes of the unit before we do our little review. And we have learned 8 tests so far to determine convergence or divergence of series. And today we're learning our final 2 tests, the ratio test and the root test. I kind of think I've saved the best for last. These are the most versatile tests, I think. They do not always work, but they work on very complicated expressions. When you see a complicated expression, these are the ones that are your go-to, all right? So before we get started, I'd like to do what I do in class is always a little warm-up, and these will come into play when we're doing the root test and the ratio test, okay? So first of all, little warm-up. Let's say first a couple problems here. I would like to find the limit as n goes to infinity of the nth root of n. The nth root of n. What is that? Okay, so it's a limit. Think of that. It's a limit. This is n to the 1 over n, right? So n to the 1 over n, so this is equal to, the limit as n goes to infinity of n to the 1 over n. As n goes to infinity, we have something going to infinity to something going to 0. That's indeterminate. But it's not L'Hopital's indeterminate. So this is going to infinity, this is going to 0. It's not equal to 0, it's just going to 0. Indeterminate. So I'd like to use L'Hopital's. But how do we get this as a fraction? Well, maybe you recall, we set y equal to this, and we take the limit of both sides. Not the limit, the natural log. The natural log of both sides. And you may or may not recall that when you take the limit, the natural log of both sides, the natural log of a limit is the same as the limit of the natural log. And that's a handy form because we can pull down the 1 over n, right? Use our natural log properties, our log properties. And I'm going to pull down that 1 over n. And now I can write that as natural log of n over n. Like that. Now when I let n go to infinity, I have infinity over infinity. So now I can use L'Hopital's, right? Okay, and for L'Hopital's here, using L'Hopital's, I'll have the derivative of natural log n over the derivative of n. Now when I let n go to infinity, I get 1 over something going to infinity, so that's 0. So natural log y is 0. Get y, so e to both sides, e to the 0 is 1. So we found out up here that the limit as n goes to infinity of the nth root of n is equal to 1. Now, you don't want to have to find that limit every time you need it. This is a great thing to memorize, okay? That's a great thing to memorize. So we found out that that's 1. Now let's do the limit as n goes to infinity of the nth root of n cubed. Let's see what that is. Is it still 1? Let's find out. Okay, so we're going to let y equal that. We're going to take the natural log of both sides. When I take the natural log of this side, I'm going to go ahead and switch the limit with the natural log. Okay, let's write this as an exponent. What's that as an exponent? The 3 is the power, the n here is the root. So this would be 3 over n, right? Okay. So use your log properties. Pull the 3 over n to the front, yeah? So that will be 3 ln of n all over n, right? Okay? So then I would have this 3 here is just a constant, right? I could take it out. I could take that out. Okay? Now I have the limit as n goes to infinity of ln of n over n, which is exactly what I had here, right? That gave me 0. So I have ln of y is 3 times 0. So y must be e to the 0, which is 1. So down here I'm going to write the limit as n goes to infinity of the nth root of n cubed is also 1. We're going to generalize in just a sec. Okay? Number 3. What do you think the limit as n goes to infinity of the nth root of n to the 10th would be? Of n cubed, it was 1. What's this one going to be? I hope you know, I hope you can see from our work what it took to do it. We would just have a 10 out there. We would still get 1 for our answer, right? We would still get 1. So what about the limit as n goes to infinity of the nth root of n to some power where p is a finite and positive number, that would be 1. Okay? All right, what about this one then? What if p is not finite? What if p is infinite? In other words, what's the nth root of what is the limit as n goes to infinity of the nth root of n to the n? Because n would be going to infinity, right? Well, let's take a look at that. This would be the limit as n goes to infinity of n to the what power? N over n. Right? That reduces to 1. Now take the limit. This is infinite. Okay? So this is 1 as long as p is finite. But if that exponent is also going to infinity, then that limit does not exist. Okay? So let's keep that in mind as we look at, specifically, that will be useful for the root test, which is why we had all these roots, right? So let's take a look at your notes that I gave you. So ratio test and root test. Okay, very useful tests. The next unit will deal with power series, which we will find have factorials and powers of n in them. Okay, so in the next unit we will use the ratio test and root test almost exclusively. Not quite exclusively, but almost. Okay, so keep that in mind. These are two really important tests for us. The ratio test is really useful if your expression has factorials in it. The root test is very useful if your expression has powers of n in it. Okay? All right. let's say that this is a series of non-zero terms. So the terms are not zero. They can be negative, they can be positive, but they're not zero. Okay? This series converges if the limit as n goes to infinity of this ratio, hence the word ratio test, it's a ratio of the n plus 1 term to the nth term. If that ratio is less than 1, then the series converges. If that ratio is larger than 1, then the series diverges. So you're going to be finding these limits and comparing them to 1. Are they greater than 1 or less than 1? Or less than 1 or greater than 1? If they're equal to 1, then the ratio test is inconclusive and you need to go use one of the other 8 tests. Do not try to use the root test if you found that the ratio test gave you a value of 1, because the root test will also give you a value of 1. These tests actually work very similarly to each other. Even though they're very different, they give you the same values. So if you get 1 for this test, you're going to be getting 1 for your root test as well. Okay? So know that. For the root test, you still take the limit. Limit and limit. It's another limit test, all right? But instead of taking a ratio, you're taking a root. Hence the difference in the names. The ratio test versus the root test. And you're taking the nth root. That's why we did those warm-ups with all of those nth roots. You're taking the nth root of the absolute value of your expression in your series. Okay? Same thing. If the limit is less than 1, the series converges. If the limit is greater than 1, then the series diverges. If the limit is equal to 1, we're inconclusive. Go use one of your other 8 tests. Do not use the ratio test. Okay. Note that the ratio test and the root test both have this absolute value in it, right? That makes it very handy to use with alternating series. So if the alternating series test looks confusing, looks like it would be confusing to use, go and use a ratio test or root test. Okay? Also a useful fact to remember. Remember that this, we just found that out. Okay? In fact, you may want to change that to the nth root of n to the p, where p is finite and positive. Finite and positive. Okay? All right. Examples. Let's determine whether each of these converges or diverges. Keep in mind, on ratio and root tests, we don't know what they converge to. If they do converge, we don't know what they converge to. We don't know. Okay? This one. So in this one, I see a power and I see a factorial. Okay? Since I see a factorial, I would like to show you the ratio test for this. Okay? So I'm going to use the ratio test. So for the ratio test, there are no conditions. You don't have to state any conditions. You just dive in and use the ratio test. Limit as n goes to infinity. The ratio test has a limit in it. You need to show me that limit or it's not the ratio test. Okay? All right. Of the absolute value of. Okay? You're going to start with the n plus 1 term. The n plus 1 term. So replace n with n plus 1. 2 to the n plus 1 divided by n plus 1 factorial. Okay? And then we're going to divide that by the nth term. So just write this down. So 2 to the n divided by n factorial. N plus 1 term divided by nth term. Okay, this is equal to the limit as n goes to infinity. I have this complex fraction, so I'm going to write it as a not complex fraction. 2 to the n plus 1 divided by n plus 1 factorial times, let's multiply by the reciprocal, right? N factorial divided by 2 to the n. Okay? Now let's reduce. Let's reduce. So I see, do you see, first of all, we're not taking a limit yet, so let me write that limit. Okay, absolute value. Okay, 2 to the n plus 1 divided by 2 to the n. Time for a piece of scratch paper. 2 to the n plus 1 divided by 2 to the n. That would be like 2 to the 8th divided by 2 to the 7th, or 2 to the 100 divided by 2 to the 99. 2 to the n plus 1 divided by 2 to the n. How will it always reduce? How do those always reduce? They reduce to 2, right? To the first. Another way you can think of that is subtract the exponents. You're dividing the same bases, you subtract the exponents. You get 2 to the first. So we're going to have 2, and it's going to be up on top because that's where our larger power was. Okay? How do these reduce? How do these factorials reduce? Well, they reduce to n plus 1 on the bottom, right? Now let n go to infinity. Now let n go to infinity. When we let n go to infinity, we get 2 divided by a very, very large number. That limit is 0. Okay, so I should have written it down here because I don't want to encroach on my number 2 over here. 0 is less than 1, isn't it? You're always going to be comparing it to 1. 0 is less than 1. Therefore, the series converges by ratio test. Okay? Not bad. Number 2. So for number 2, do you see the powers of n? See the powers of n? And I don't see any factorials. So I'm going to use a root test. Okay? It looks complicated. I'm going to use a root test. Okay? So, root test. Again, there's no conditions. We just dive in. Well, the condition is that they're non-zero, but there are no 0 terms in here. Okay? So we're going to dive in and use the root test. The root test also has a limit. So start with your limit. It's not a root test if you don't show me a limit. Okay? And then you're doing the nth root of the absolute value of just your n expression. Just your n expression. Okay? So let's see what's going on here. Let's think of this nth root. So this would be the nth root of n squared times, and I like to think of it like that. You could put 2 over n, and that's fine too. That's fine too. But I like to look at it this way because I can use this piece of information that we know. I know that this piece is going to 1. All right? This piece, though, I'm going to write that as 3 to the n plus 1 over n plus 1 over n, all over 2 to the n over n. Okay? This piece is going to 1. As n goes to infinity, what is the exponent going to? 1. The plus 1 doesn't matter. The n's reduced to 1. So this is going to 3. What's this piece going to? 2. So this is all going to 3 over 2. Is 3 over 2 greater than 1 or less than 1? Well, it's greater than 1. So this series diverges by ratio test. Oh, not ratio, root. We did the root test. We could have done the ratio test on there too. You can always do both. I could have used the root test here. I could have used the ratio test here. Okay? That's fine. Okay. This one. I see a factorial, so I'm going to use the ratio test. Okay? I'm going to use the ratio test. So let me switch colors again. Ratio test. Limit n goes to infinity. Okay? Absolute value. So since it's the absolute value, I don't have to worry about that -1, because what's the absolute value of -1 to any power? Just 1, right? So leave it off. Don't put it in here, it'll just mess you up. So we're going to begin by replacing every n with n plus 1. When I replace this n with n plus 1, I get n plus 2 inside that parentheses, right? So I'll have n plus 2 factorial. Okay? Divided by 3 to the n plus 1. Now I'm dividing by the nth term, which is the same as multiplying by the reciprocal of that a sub n. So I'm just saving myself a step and writing that as my ratio test. Okay? Let's work out this limit. Let's reduce what we can. I see these factorials. What do they reduce to? They reduce to an n plus 2 on top, don't they? What do the 3's reduce to? The 3's reduce to a single 3 on the bottom. Take the limit. What's the limit? As n goes to infinity, this goes to infinity. Is that bigger than 1? A little bit. So this series diverges by ratio test. Could have used a root test too. Okay. Number 4. See this big power of n? This is perfect. Perfect for the root test. So I'm going to use the root test. Limit n goes to infinity, nth root, absolute value of just what you see here. 2 to the n plus 4 over 3n all to the n. What happens to that power? The nth root of something to the n power is just what's inside, right? So we get the absolute value 2n plus 4 over 3n. Now let n go to infinity. As n goes to infinity, the plus 4 is insignificant, and the n's reduce, and we get 2/3. Compare that to 1. This is less than 1, so this series converges by root test. Now number 5. I see powers of n. I see powers of n. So limit n goes to infinity, root test. Nth root, absolute value of what you see there. E to the 2n divided by n to the n. Okay? Simplify and then take your limit. So this nth root, it goes to the bottom of each of these exponents, right? And we're going to have e to the 2nd divided by n. Let n go to infinity. This goes to 0, which is less than 1. So this converges by root test. Okay? Okay, one more here. Number 6. Again, I see a power of n. I'm going to use the root test. I could use the ratio test. Would you like me to use the ratio test? Huh. I think I would use the root test, but you can use the ratio test if you prefer. But I would use the root test. I kind of like the root test better. To me, it's a little bit simpler. But the ratio test is fantastic as well. Whatever. I'm going to use the root test though. Alright, root test. Nth root of absolute value of what I see. Okay? Now, let's simplify a hair and then take the limit. So this is going to be 9n minus 2. That's going to be nth root of 9n minus 2, right? Over the nth root of n times 3, because it's n over n. Well, remember that the nth root of a polynomial goes to 1, right? So this nth root here goes to 1. Let me close my absolute values. This nth root here goes to 1. This nth root also goes to 1. And 3 is 3. So this is 1/3, which is less than 1. So this also converges by root test. Okay? Before we do anything else, I want to make note of something here. In example 1, let me get a different color. Let me get a blue. Alright, in this one, do you remember when we were talking about powers of infinity? And I said that the biggest one that we deal with is n to the n, and I called that Big Daddy. It's the strongest one that we deal with. The next one is n factorial, and I said that's Big Mama. Mama. 2 m's? I don't know. Okay, Mama. Maybe with an O. Anyway, whatever. The next one is some number to the n power. E to the n, 5 to the n, 3 to the n, something like that. And then we had all of our polynomials. N squared, n cubed, and whatever, n to whatever. Okay? And then bringing up the rear is little natural log n. And those were the powers of infinity. So look at this. Do you see Big Mama? Big Mama's in the house, and she's sitting in that denominator. What's she going to do to that fraction? She's going to pull it down next to the x-axis really fast. So of course it's going to converge. Of course it converged. It makes sense that it did. We prove it using the ratio test or root test. But of course it's going to converge, you guys. that n factorial is so strong. If I graphed it, you'd see it just pulls it straight down. Okay? Here we don't have a factorial or an n factorial or an n to the n. We do have the next in line, which is 3 to the n plus 1 over 2 to the n. This is less powerful. It's going to have less of an influence. What's going to influence it is this 3 over the 2. That's going to influence it. Look what our limit was. Kind of makes sense. Kind of makes sense. Over here, our limit was 0. Here, our limit was 3/2. Okay? Look over here at number 3. What's your strongest thing there? What's your strongest infinity in the factorial again? The factorial was stronger. Big Mama. Big Mama's in the house. Okay? And she's sitting up on top of that fraction. What's she going to do? She's going to send that guy to infinity. Okay? All right? Diverged. This one. Here we've got a 2 to the n. I'm sorry, a 2n to the n, and we got a 3n to the n. Both good, strong powers. So what do we get? We got 2/3 here. Which one is power? One of these is more powerful than the other? N to the n, Big Daddy. And he's sitting in the bottom. He's going to pull that thing down to 0 so fast, e to the n doesn't know what hit her. Okay? So of course this is going to converge. Okay? Here, the 3 to the n is going to rule the roost. It's going to rule. So these powers of infinity, when you get used to them, they make a lot of sense, and they make these more obvious. Okay? I say this stuff to you because if you're taking a multiple choice test, you can use these concepts. All right? And you don't have to spend time writing out work that you may not need to determine convergence or divergence. Okay? All right. But in a free response question, I must see your work. Okay? I need to see the work. I'm getting you ready for the AP test where they're going to insist on work if it's an FRQ. They're not going to say, oh, he probably knew that. No, they're not going to say that. If the work's not there, you get nothing. It's called a bald answer. All right. Go try the practice problems in the worksheet and see how you do. Send me questions.